right, good evening, everyone. Thank you for joining us for the third annual Ronald H. and Mary E. Simon Actuarial Science Lecture. My name is Becky Jo Farrington. I'm working for the College of Natural Science here at Michigan State, and I'd like to welcome everybody and joining us here at the Kellogg Center and those watching online via the MSU Alumni Association's live stream. This lecture and other great programming from Michigan State can be viewed on demand at alumni.msu.edu/live stream. Thank you to the Alumni Association for bringing enriching programming like this to the entire Spartan Nation. I'd now like to introduce to you Dr. Emil Valdez, Director of the Actuarial Science Program at Michigan State University.
Thank you, Becky Jo. Appreciate that. Thank you all for coming tonight. I'm here to introduce Mr. Ron Simon. Ron and his wife, Mary, and the Actuarial Science Program are the reasons why we are gathered here tonight, to learn and be inspired. So both of them now share a passion of giving back to the community as well as back to Michigan State University. Ron completed his bachelor's degree in mathematics from Michigan State University, and he has always recognized the value of his education at MSU. Ron retired from Auto Honors Insurance Company in 2010, where he last served as the CEO. He has worked for Auto Honors for 44 years, starting with their IT, computer science area, leading an actuarial department, and later serving as treasurer, president, and CEO of Auto Honors. We are very thankful to Ron and Mary Simon for establishing an endowment at MSU to support the actuarial program. This endowment includes funding the Actuarial Science Lecture Series. We are also grateful to Ron for the many other ways that he continued to help the actuarial program. For instance, this year, Ron is providing guidance and assistance in completing a group project on the pension system of the city of Lansing through our Math 491B course on teamwork experience. Our 491B is one of the most unique courses that we offer in the program that many other schools do not have. It is an opportunity for our students to be exposed to practical work experience. Please help me in welcoming Mr. Ron Simon.
Thank you, Emil. And thank you, everybody, for coming tonight. I hope you have had an enjoyable evening so far. Truly, we've saved the best for last, having Karen Clark here tonight. I first met Karen a year after Hurricane Andrew struck in Florida. And that was in 1992. Hurricane Andrew, many don't know, but actually caused the bankruptcy of many insurance companies who did business down in Florida. And had the hurricane been another 50 or 75 miles north further, it caused the bankruptcy of several more companies. So as a result of the event, Hurricane Andrew, in 1993, auto owners submitted our data to AIR and Karen Clark to do the modeling of catastrophe events such as hurricane, tornado, and earthquake, and did a remarkable job, opened our eyes very wide as to what our exposures were. So I'm very proud to say that I have known and been associated with Karen for all of these years. Karen is a serial entrepreneur whose leading expertise in catastrophe risk analysis and management. In the late 1980s, realizing the insurance industry needed better ways to estimate catastrophe losses, she formed a company called Applied Insurance Research, AIR, where she developed the first catastrophe model. Karen grew AIR to be one of the top 2 leading modeling companies in the United States. And I think that's understating it, because in my opinion it was the top 1 company in the United States. And in that process of developing this company and working with it and creating standardized technology for catastrophe analysis, ultimately she sold this company to ISO in 2002. In 2007, she founded a new company, Karen Clark. She co-founded a new company, Karen Clark and Company, to develop and bring to the market advanced tools for the next generation catastrophe risk technology. In the same year, Karen was honored with an award certificate from the Nobel Peace Prize bestowed on the Intergovernmental Panel for Climate Change. She was an early supporter of the IPCC. Karen is globally recognized as an innovator in the insurance industry, including Woman of the Year in 2001. Also, she was awarded the most influential woman in the reinsurance industry in 2008. She was recognized, she was recently recognized by Reaction Magazine as the 14th most influential person in the insurance industry over the past 30 years, and further recognized by National Underwriter as the 6th most influential living legend. With that, I am very, very pleased to introduce Karen Clark. Thank you very much for being here with us tonight.
Well, good evening to all of you, and thank you, Ron, for that very kind introduction. It is truly an honor to be here. I'm really honored to be part of this program tonight. As Ron indicated, I've known Ron for many years and his colleagues at Auto Owners, and I think what Ron failed to let you know during the introduction is that Auto Owners, and particularly spearheaded by Ron, was one of the first insurance companies that engaged us to do the modeling, because believe it or not, it's hard to believe it now, but it was hard to convince people that they needed the models. And so I would say, as long as I've known Ron, which was a long time, he's always been a forward thinker. And I think this lecture series is another example of that. So I'm very, very honored to be here and be with Ron and all of you. They say, I guess, when you're giving a talk, that at best people hear about 50% of what you say. And that's actually good, because some of you were at the afternoon lecture today. So I hope that the 50% that you didn't hear this afternoon is the 50% I'm going to give tonight. So, so you'll hopefully still enjoy the talk. And I think after the great food and drinks, hopefully you will. So, and I can't think of a better dinner topic than catastrophes, right? I mean, what fun are we going to have here? Let's have some indigestion here. So before we get into the modeling, which of course at this year I'm not going to go into a lot of the details of the modeling, I wanted to start out talking a little bit about catastrophes. I mean, we all know, we can all relate to that. I mean, it's on the news all the time. I mean, the hurricanes, the earthquakes, the tsunamis, happening all over the world. So I thought it would be interesting to just start out with some information on globally. Again, CAT modeling is a global, catastrophes are global. If we think about kind of like the large loss potential, the 1 in 100 on a global basis, we look at the global catastrophe risk. How do you think it splits up? and I should say the insured catastrophe list, because you know there's a difference, of course, between economic losses and insured. Catastrophe modeling is for insurance companies. But if we think about the global insured catastrophe losses, like just think in your minds a little bit about how much would be from the US, Japan, China, India, all these places. So, all right, so you got your number in your mind, right? Well, here's how it breaks down, which may or may not surprise some of you, but on a global basis, half the catastrophe risk is from the US. And you can see the little, and again, this is because of insured. Japan has pretty big slices, their typhoon and earthquake risk, Europe, and then the rest of the world is that light blue, mainly because there's a lack of insurance in a lot of the other places that are prone to catastrophes. But look at the US and look at hurricane. Hurricane is almost a third of the US hurricane of the global. And another interesting statistic is that of that hurricane, about half is the state of Florida. So I actually think that it's an amazing statistic that the global catastrophe risk, almost a quarter of it is due to Florida, the state of Florida. So I don't know, that may be good news for the rest of the states, but you know, it's not good for them. So, I have a quiz for you now. I like to have a quiz for you too. So we all know hurricanes, and hurricanes are a lot in the news. And of course, with climate change, there's a lot of, every time there's a major hurricane, of course, it's a record breaker on losses, and it's, of course, due to climate change. It's proof, right, that we have that. Well, how many of you think that losses from hurricanes are increasing? You're thinking you're good, all wise on me, aren't you? Because you took a peek at that next slide. Well, on a nominal basis, if you just look at the actual losses, of course, they are rising. But if you look on a normalized basis and you look at what past hurricanes would cause based on today's property values, you see there is absolutely no upward trend. And in fact, the biggest spike, which is over 180 billion, that's economic, insured would be about 125 billion, is from a 1926, which was the Great Miami Hurricane of 1926. And which we don't hear about because, of course, no one lived in Miami at that point in time. So you see that even Katrina or 2005 doesn't show up. So really, as far as climate goes, and this is confirmed, and I'm sure, how many of you have read the new IPCC report is out, 500 pages of fine print. I'm sure you've read it, right, already? Right, so they actually agree. So if you actually read what they say, they agree that to date, there is no evidence that we can say climate change has had any impact on hurricane activity. And it's really us, we the people, who are actually causing the losses to increase. In fact, we have a rule of thumb in the decades, I hate to admit how many, I've been in the cat modeling world, that about every 10 years, the loss potential in the US doubles, purely due to demographics. Because what do we do? Well, this is an aerial shot of Miami in 1920, and this is an aerial shot of Miami in currently. And of course, it's not just, I travel to Europe a lot, and I heard someone say, like, Americans don't like to live near the water, they like to live on the water. And I think we have some proof of that. Look at what we're building, literally, right on the water there. So we are causing these record losses every year. So when climate change kicks in, which it may at some future point, that's only going to add to what we're doing. So we got an enormous problem here. And as I said, that Miami storm was just a Cat 4. That would be, as we said, about 125 billion insured. Well, what if we had a Cat 5 hit this area, hit right down there? What would that be? Any guesses? Those of you who are quick and saw the other chart? Well, it would be about double. So it would be about 250 billion if we have a Cat 5 hit Miami. And that would not, why would we wouldn't be surprised by that, right? Andrew was a Cat 5, but as Ron said, Andrew luckily hit well south of Miami. So if Andrew would have hit Miami, it would have been about 60 billion. Everybody knows that. Now you can do the math. You double to 2002, that's 120, and then you double again. Now that's 240 billion. So we have not seen anything yet in terms of what we could have in terms of losses. This picture, what it's showing you are for different landfall points going from Texas all the way up to Cape Cod, the 100-year hurricane, what the insured losses would be for the industry as a whole. So you see, of course, Miami's the biggest spike. The next is Galveston, Houston. That would be about 150 billion from a Cat 5. In the Northeast, you see a little skinny little line there. That's about $150 billion industry loss. That wouldn't even be a Cat 4 or a 5, a Cat 3. Only a Cat 3 taking the track of Hurricane Irene in 2011 will cause about almost 150 billion. And then you see Tampa and what have you. So even without any impacts of climate change, we have a huge potential in the U.S. for losses. And so what the models are supposed to do, of course, is to help companies manage this loss potential and help them make sure that they can survive when the big one actually happens. But we're very brave in the U.S., and we don't let Mother Nature scare us at all. So, of course, the other potential impact of climate change is sea level rise, right? So, well, what do we do about sea level rise? Well, who's afraid of sea level rise? Because we innovate, right? We can build for sea level rise. So we're not going to worry about that one either. So with the American ingenuity. So we've got a real issue. Now, how do the models work? And again, I'm not going to go into the nitty-gritty details of the models, but I know many of you are not familiar with them, so I'll just give you a little background of how they work and why they're so important. They're all this is the actuarial program. Now, I'm not an actuary. I'm actually not even a scientist, but as Ron said, I built the first catastrophe model, and this is helping insurers estimate losses. So why didn't actuaries do this? In fact, I know many actuaries. I'm friends with many, and one of them always says to me, "I'm so mad you did that first CAT model. We should have done that. The actuary should have done it." Well, why didn't you? Because you needed to think in a different way, because the problem, or the good thing about catastrophes is that they're infrequent, so there's not a lot of data. So the idea behind the first model that I created is, how can we create data? We take some limited historical data, we put a nice little distribution on it, be it a Weibull or a log norm or something like that. I won't go into all the details. And then we're going to use that to do just this plain and simple Monte Carlo simulation. And we're going to now look at all kinds of different hurricanes, where they can make landfall. We're going to look at the historical data. That's step one. Then we do need to bring the meteorologists in. So this is where it gets a little scary for the actuaries. We need those scientists out there to give us the formulas that if we do have a Cat 5 in Miami, what is the footprint going to look like? What are the wind speeds going to be? How far are they going to extend inland? That's step two. Then step three is, of course, well, how much damage are we going to have? If 100-mile-an-hour winds, hits one of those buildings there, how much is the damage going to be? And then the fourth component is the insurance information that we love, the policy conditions. Well, we have deductibles and we have limits, and so what is the actual ultimate insured loss going to be? So that's it. It's as simple as that. And there's this big mystique, which I'll talk about the CAT models and how actuaries just can't go there because, they're way too complicated. Well, actually, that's not true. Okay, these are statistical models, just like models you deal with all the time. And in fact, what I'm going to invite you to do over the upcoming years is to get more and more involved in this area because you're needed, and I'll explain why. So basically, and if you're doing earthquakes, hurricanes, tornadoes, any peril, it has exactly the same structure. So they're all exactly the same. You get you simulate, this is your Monte Carlo simulation, a year, an event ID, and a loss. And then you get the almighty exceedance probability curve. which is a very fun thing to talk about because there's so much misinterpretation of this curve. But basically what that is, and it comes out of the model in this nice little line there where it shows you, or it shows an insurance company like auto owners, for any loss amount, let's say for 100 million, 500 million, what's the probability of you reaching or exceeding that loss amount? So basically they're designed to give more than just a scenario loss, but what are the probabilities? And what's become extremely important is this 1 in 100 and 1 in 250. Okay, now in the early days that Ron talks about, the models were used for very limited purposes, for reinsurance underwriting, for auto owners to say, well, maybe how much reinsurance do I want to buy? But over time, they have become way more important. So AM Best, S&P, Moody's, they ask companies for these 1 in 100 point estimates. The point, what is the number? It's 183 million and 56 cents. And yes, we have delusional exactitude coming out of the models because you can get all this false precision and you can have I've seen model output with 10 digits to the right of the decimal point. And I'm like, geez, that's a real accurate model you got there. So they, basically dwell on these numbers, and it's very important because that determines how much capital you need. That determines the return on your capital. It is amazingly, important for those numbers. And it can cause, anybody in the cat modeling world ever heard of the RMS, that was AIR's competitor, version 11? They had a model version that for major companies, that 1 in 100 number doubled or more. The industry went ballistic. It's like, what is going on? So, and I think that was the start of realizing we cannot base our decisions on that number from a black box. If we are basing it on it, you better have an open box where you can see those assumptions, and we'll get to that. Well, why did the models become so powerful? Well, the main reason is because computers became so powerful. Here is a picture. Those of you who are kind of at our vintage here will remind these. Half of you in this room have no idea, what in the heck is that? Well, that is called an IBM mainframe computer. That the first cat models in the mid-'80s ran on these things. And Ron's data at auto owners were on these things. 9-track tapes. So auto owners would have 1 row of one of that rack to do their data. This is what it came on. My early days, I had to use these computers for the first hurricane model. So of course I had a lot of fun. These things were being shipped to me. I had to put them in my car. I had to drive to a place that had these computers, hand them to the guys, go back and run them. So the first computer I could actually bring in-house was called a Sun Spark Server 390. Is there anybody who knows anything about that? Well, it cost $60,000, and it weighed 700 pounds, and it had 1 gigabyte of hard disk and 16 meg of RAM. Now you figure. And that is the truth. I've got the specs. I still got that computer, believe it or not. I lug this thing around. I paid to have this moved from things because it's just such a conversation piece. When people come into the office, what is that thing? So because computers have become so fast, and now instead of doing the first model, we did 1,000 Monte Carlo runs. 1,000 was a lot. Now the models can do 1,000,000 runs, so obviously they're getting more accurate, right? Because I'm doing all these things. Well, no, they're not. You're just getting more and more precision on a wrong number because, it's not. So this is, you all know this, Moore's Law, blah, 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 how fast computers have become now. But in reality, it doesn't matter. You can do 1 billion simulations on the fastest computer. You're not getting rid of the fundamental uncertainty around the EP curve because there are things that scientists just don't know, and they will never know. And I'm going to talk about those. the probabilities of large events in different geographic regions. We'll talk about hurricanes and earthquakes. Unknowledge, we've coined a term, our unknowledge with respect to how the ground will shake when there's a new Madrid earthquake. The unknowledge about how these buildings are going to experience that ground motion and how they're going to fare. So if there's one thing you take away from this, it's the last bullet there. The models will never be accurate. Okay? So just keep that in mind, because people forget that. Because if you go to a modeler presentation and all the scientists come up, they've got animations, they've got this, that, you just get so wowed. You think, oh my goodness, we know so much, but we don't. What we don't know is much more than what we know. Every major event is a surprise. Somebody mentioned this afternoon the tsunami in Japan from Tohoku in 2011. That was a magnitude 9 earthquake in an area where all the scientists said there could not be a 9 there. You could only have an 8.5. I won't go into why. We were wrong. There was a 9 there. So when you're using these models, you keep in mind what you have are not scientific facts. You have scientific opinion, okay? Which is very valuable, but it's not facts. So you got to keep that in mind. Now I'm going to show it to you. Let's talk a little bit about hurricanes first. So that version 11, where the whole thing went ballistic, a lot of this changes the problem. It's not new facts, it's just new opinions. So some scientists at RMS decided they were going to change some assumptions and didn't realize what impact that was going to have on the loss estimates. So the idea is we can't eliminate the uncertainty. So how do we can't make the models better. At KCC, we have a new loss modeling platform. I think it is better than AI/RMS, but it's not the science or the engineering that's better, it's the packaging, and I'm going to tell you why that is. So let's talk about hurricane first. So here you are. Okay, a lot of actuaries in here. We're going to have a lot of fun now. We're going to build our Northeast hurricane model. Okay, so we're going to go and get all the data that's available for Northeast hurricane, and there it is. We have 9 landfalling events since 1900. That's it. That's all we have. And the red ones mean there's still a lot of uncertainty as to even what the peak wind speeds were for those storms, because we did not have anemometers out there in 1954 or 1938 even, or 1944. So those are our best guesses at what the intensities were of those hurricanes. So what do you do when you're building a model? Well, you do a simple actuary. You just extrapolate from the data. No more secret than that. So what we're seeing is I've just kind of I kind of just sorted the wind speeds and just kind of, that's a log scale on the x-axis, just kind of said, okay, well, the largest one in 100 years is about a 100-year return period. But of course, what insurance companies want to know is, well, but what's the probability of a Cat 4 in the Northeast? All right, you tell me, what's the probability of a Cat 4 in the Northeast? But that's what the models tell you. The models are even going to tell you what's the probability of a Cat 5 in the Northeast, because that's what insurers want to be told. What is that information? So the modelers, and there are actually 3 modelers out there. I tell Ron, although one is tiny, so they don't count that much. So I always put 3 lines. So you got 3 different modelers. You're going to get 3 different extrapolations. So which one is right? Well, I mean, we can sit here till the cows come home, and we don't know which one is right. So the idea, so in the old models, they were black boxes. Actuaries we all bowed and said, whatever comes out of the model is the truth. And when it changed, we thought there was a new truth, but it isn't. It's just somebody decided that they're going to change the assumptions in there. So we've got to look at these models differently, not to change the science. This is all the science we have. But basically, our new philosophy is the scientists give you their opinions and you make the decisions. Okay? So you see, and you can go talk to whatever scientists you want. Some are going to tell you adamantly it's a 100-year return period, and I know it is because blah, blah, blah. There's another one that's going to say, I know it's 500 years. So they all know what they know. Right? So your job is to just sort through all that and say, well, do I want to be conservative in the Northeast, or do I want to be aggressive? And then when you lock it down, it can stay that way. You can have consistency. You don't have a model kind of, jerking around your very important decisions, and AM Best telling you, oh, now you need a lot more capital. So the idea behind the new models we're developing is not that they're different underlying, but it's a different way for actuaries and users to interact with the models by actually seeing what's in there and then determining for yourself what assumptions your company should be using. Okay, we're in the central US, so we have to talk about New Madrid earthquakes. Talk a little bit about that. So what do scientists know about the 18, 11, 12 earthquakes? All the scientists put together, what do they know? All they know is that something big happened because the data is from personal accounts, journals, wood carvings. There's no actual data. So scientists, of course, don't know the magnitude. So what they do is, what scientists do, you will be surprised, is they actually go and find old newspapers. And they find accounts that people wrote of the damage. And they convert that to an MMI intensity. And I'll explain. I know today, I know a lot of people don't know what MMI intensity is, so I'll just explain that. Someone asked this afternoon, well, what's the difference between that and what I hear, the Richter magnitude? Well, the Richter magnitude is a one measure of the energy released from the earthquake. The MMI intensity is the ground motion that's felt all around the earthquake. So at every location, you have a different MMI intensity. And 12 is the largest you can get. And basically what that is you are, the scientists are inferring the intensity from the damage. And you're saying, well, that's opposite. We're supposed to calculate the damage from the intensity. But it's weird, actually. It's actually, but that's how they do tornadoes too. Nobody's out there standing in a tornado measuring the wind speed, right? What they're doing is, actually some crazy people do probably, but they're actually looking at the damage afterwards and saying that was in F5, that was in F4. It's the same with earthquakes, you'd be amazed. So basically what scientists do, every 6 years the USGS puts out a new report. This shows two different reports, to 1996 and 2002, two debating scientists. Johnston has felt that in 96, because church bells rang in Boston, sidewalks cracked in New York, it had to be a magnitude 8, because only a magnitude 8 could extend that far. But this Suhoff, his colleague at the USGS, decided that no, that was because of bad soil, so probably it wasn't an 8. It could have been an 8, but we'll give that a 15% probability and then give other probabilities for lower magnitude events. So they're getting a lot smarter about what they don't know, right? So what do you think the 2000, and that's the truth. It's, we're getting smarter about what we don't know, which is very good. So in the 2008 report, they got very smart and created this huge logic tree that shows we don't know nothing about this. We don't even know if this is going to be one major event that happens or multiple smaller events. And that makes a huge difference for the damage. So we'll give that clustered or not 50-50 weight. We go over, there's no surface representation of the New Madrid fault. So the only way scientists kind of figure out where it is from what's called microseismicity. And those are the little earthquakes that happen a lot, the 3s and the 4s. There are actually quite a few that happen. So they plot that, but there's uncertainty. So they give different areas. The recurrence models now, I think they go from 500 years to 1,500 years, and the magnitude goes from 7.1 to 8.0. And you don't even want to talk about the ground motion over there, how different those are. So with all this logic tree, you get a CAT model. Auto owners gets their CAT model and magically tells auto owners that your 1 in 100-year loss is $183,000,056. And now, isn't that informative? That's so informative. I mean, I get a lot of that. Because I can guarantee you when that earthquake happens, your loss is not going to be 186 million. It's either going to be really small or it's going to be a couple billion. Because if you go through either any of these different ends of the logic tree, you are going to get a factor of at least 10, probably more, between the low end and the high end. So again, the idea behind the new open platform is you should see what your losses would be if it is a 7.1 or if it's an 8.0. And how do you feel about that? You know, how do you want to manage based on that? So the idea is to give you visibility on how these different assumptions matter versus giving you a number, okay, which is just virtually meaningless, actually. So I've been studying this for a long time because it's very curious to me, because many of you are probably thinking, well, we know there's uncertainty, and everybody knows that, but despite that, we still expect the models to give a number. So I've really been studying this for a long time, and I finally found someone who had the answer to this, and that's Dilbert. So what Dilbert says, those of you who can't read this, is said, I didn't have any accurate numbers, so I just made up this one. Studies have shown that accurate numbers aren't any more useful than ones you make up. How many studies showed that? 87. No. So I think this hits the nail on the head because I have a true story for you. Okay, as I told you, every event is a surprise. So anybody know the last major earthquake we had in California? Northridge, 1994. If you remember that, it was a surprise again, like Tohoku, to the whole scientific community. Why was it a surprise? For two main reasons. One is there was a lot more damage to wood frame structures than the engineers thought, because wood frame is flexible, so it shouldn't have a lot of damage, but there was a lot of residential damage. And the other thing is because it happened on an unknown fault. And scientists didn't know that a magnitude that large could happen there. So a few weeks after the Northridge event, I and one of my colleagues from AIR, we went to the California Department of Insurance, and we were making a presentation about Northridge and how it happened on an unknown fault. So there's a question. Yes, what's your question? How many unknown faults are there? And at the California Department, no, our engineer said 113. And at the department, they're not as smart as all of you. They obviously did not go to Michigan State because it took them about 15 seconds before they laughed after he said 113. So it took them a little bit longer to get on it. So anyway, I think that's how Dilbert is. So we need the models to give a number. We're not going to get away from that. You need a number. AM Best needs a number. Okay. But the difference is it should be your number, not a secret little box that's going to spit out a number at you. You should know and have control over that number. So everyone wants a number, and as I said earlier, it probably didn't matter in the early days that you had a black box, because you weren't really, I mean, even, I don't know, Ron, how seriously you took the model in 1993. Maybe you did. What was after Andrew, that's true. Well, some companies, it took them longer. As I said, people in Michigan are definitely smarter than a lot of the rest of the population, because there were still companies in Florida that did not take it seriously even after Andrew. Why? Oh, well, Andrew was a 50-year event, so we don't need to worry about it for another 49 years. So that was kind of the thinking. That was the insurance commissioner, right? Wishful thinking, right? So, but today, these models are critically important. They are used for such important decisions. Not only how much capital companies need, but companies are trying to use them to, say, individually underwrite in specific buildings. So they want to know, this building, what's the rate on this versus the next one? Now, if you think the PML is volatile when scientists change their mind, you look at the losses at one location. They go all over the place. And I've had underwriters get so frustrated, they say, I don't care if it's a good risk or a bad risk, just make up your darn mind. You know, so that's what we need. We need more consistency. So nobody knows. But if you control those assumptions, you as actuaries, you got to pick up the hood, look at those assumptions, explain them to your CEO, explain them to senior management, and say, okay, this is a range of assumptions. Now, if we use this set, this is what our portfolio looks like. If we use this, now where do we want to be? And then you have to, and I get some companies too, they like the scapegoats at the models. Yeah, we like to blame it on the models, but you know, we need to get over it and you know, take on the responsibility for these particular assumptions. So the first generation models are just not well suited to the current uses. So if we are going to use models for all of those purposes. We need different models, not different science. We can't change that. We've got the best we have, not in engineering, but we need models that are open, and transparent, and that you can customize. There's only one. Anybody want to throw out here? And people from the afternoon, you're cheating, don't say a thing. But if there's big data, everybody's into big data. Okay, what would the big data be for a CAT model if you're refining it? Well, the only big data is actually the claims data when you actually pay a loss, right? So that's where you get the millions of claims. Well, hopefully one company doesn't, but the industry has millions of claims. But that's your big data. So actually, as actuaries, if you can lift up the hood and you can actually see the damage functions, what is the model saying for a 100-mile wind speed against that? And you actually have claims data, you can do your own fine-tuning. In fact, the older models are going to be in trouble because most companies, we have top 10 P&C companies and reinsurers using our new open model. They don't want to send their data to third parties anymore. That's their proprietary big data. So we need, I got a little ahead of myself, so we need model assumptions that you can see and customize. So again, scientists give you their opinions, you make the decisions on event frequency, severity, damage functions. So the advantages is for the first time you really see the exact drivers of your loss potential. You control the set of assumptions, and you can test new scientific research. Let's go back to the magnitude 9 in Tohoku. Okay, the scientists got it wrong. Okay, but that's okay because now they can just write new papers as to why they were wrong, and they can probably get tenure off of that. So that's fine. So they're good, they're just writing their new papers on this. Well, a new paper has come out that says, I won't go into the details, but that magnitude 9s can happen in more places than scientists thought. One could be the San Andreas fault in California. Now, it's just a research paper. It's just someone's theory. In the old days, your CEO or somebody senior would read that, and they'd call you up if you're a CAT model. I just read this. There could be a 9 on them. What do you think? And then you would call up AIR and RMS, and you'd say, well, what do you think? And they'd say, well, we're working on it. We're working on it. We'll give you an update in a couple years. And then AIR will have an 8.8 magnitude in their new, and RMS will have an 8.9. And then they'll argue about who's right. And then there'll be this huge, you'll spend all this time trying to figure out, is it 8.8 or is it 8.9? You know the answer, right? Who in the heck knows? So none of these people know. What you can do in an open model in our new Riskinsight is that you can say, oh, that's interesting research. I can go to my open model and I can create a magnitude 9. I can do, you actuaries, and I can prove it to any of you who doubt it. You can call me later and I can show you how you can do it. You can put in a 9, estimate the ground motion, recalculate your losses, and you can go back to your CEO in about a day and say, well, nobody knows if this is right, but if it is right, this is what it means for our portfolio. Now, that is a proper use of a model, to say, what is the sensitivity? What if these scientists are right? This would be the losses. And that's really the power, and that's the power you are going to have with this next generation of models, where you really understand the underlying assumptions and can really understand the risk versus just looking at the output. So as I said, so the open loss modeling platform, which we have out, is like AIR or RMS, but it's fully transparent, and it has people, you're going to say, well, that sounds really scary. How can I build my own earthquake? Because there are built-in modules that will generate the ground motion for you. So Riskinsight is smart enough to say, if you put a 9, then it's going to know how to rupture the fault and how to do the ground motion, and all of that will be in there with these nice little modules that are very easy to use and perfectly suitable for actuaries to use. The damage rates manager, make it easy for you to fine-tune your damage functions. So my last slide, my exciting conclusion, hopefully for actuaries, is that there's a paradigm shift. It means more interesting stuff for you. CAT modeling is here to stay. It's very important. I hope some of you will decide to embrace it. The old way, you have the scientists, they have their secret sauce, they put it into the black box, Then you get this little output curve and try to figure out, whether you believe that or not. Whereas in the new paradigm, you converse, you interact with the scientists, and then you decide what you want to put in your open box, and you can vary that. So hopefully that's interesting for some of you to look at for career choices. So thank you very much. Do I take questions? Oh, all right.
Do we have any questions for Karen?
Anyone? Okay.
Make them easy now. It's after dinner.
It's personal, so it should be easy. You said you're neither an actuary nor a scientist. I was just curious to know what your background is.
Well, I'm actually an economist, and I have a master's in economics and an MBA. And how did I end up in this is that I was more like a mathematical economist, and you saw those big computers there. What I really liked in graduate school was building models on those clunky computers. So, and to me, it was just the modeling. And in economics is a very kind of a general, social science. So it's a good preparation for something like this, because I just like taking data from different disciplines and basically building a model, which, so if any of you, or I said in the afternoon, it's great, it's kind of like actuaries who decide not to go to be like the FCAS or that kind of route, but you would like something that's more, broad or, looking across different disciplines. It would be great because you need the mathematical background, but you also need more of I think it would be good to have more of a generalist type of interest.
See, right now, companies can go to AM Best and say, well, AIR says this is what it's going to cost us. Now, if you have the open models, we going to have to explain how we came up with that. We can't blame it on AIR anymore.
Well, we still give you that scapegoat. Because we know you guys, so in Riskinsight, you have a reference model. And we've been conversing with AM Best and S&P, so they know what we're doing. So in Riskinsight, you have a reference model. So you basically start with a model like AIR or RMS. And then if you want to tweak it or do any customization, you could just go to AM Best and say, this is our reference model, and then this is our customized model. They're not going to let you get away with a fully, they're going to want to see how you've modified the model. Yeah, but I want to pick up in all seriousness the rating agencies. We've talked to them, over and over, and it sounds like they require you to use AIR or RMS, but they really don't. And what they really want to see is that you're using multiple tools and multiple approaches to understand your risk. And I know Tony Diodato said to me just, within the past several months that there are companies that he thinks has the best risk management, and they don't even use models. So the more tools you use, the better you'll look to the rating agencies.
Other questions? Any questions from the audience? Going once, twice. Okay, with that, let's give a round of applause to Karen.